Before we get into setting up the rigid body simulation for our specific shot, let's first go over some of the general principles behind setting up a bullet rigid body sim, just so you know a lot of the options that you have at your disposal. Now here, I've imported the active geometry, not the cloth-driven version, just the regular straight-up fracture, and I've blasted away the bottom just so that we're working with a smaller section of it to keep things fast. And we can start setting up our rigid body simulation by dropping in a DOP network node. We don't need to connect our active geometry here directly into that node because we'll be referencing the SOP directly from within the DOPNet. And let's create a null on our active geometry just so that we have a node to reference to set up the rigid objects. I'll just call this out active pieces. Now if you dive in the DOPNet, we're going to build this from scratch rather than using any of the shelf tools, just so you understand how it's all hooked up a little bit better. Right now, by default, we just have an output node, and we can start by dropping in the solver. So let's create a bullet solver node, and let's also create an RBD packed object node. So this RBD packed object will take a SOP reference to the packed geometry that represents our fractured object that we'll be simulating. So let's point that SOP path to our out active pieces node, and then we'll wire that into the bullet RBD solver and connect that to the output. And then let's go back outside of this DOPNet, and we'll set our simulation parameters on the simulation tab. And we want this to start at 1047. And then if we rewind to the beginning of the time slider and then display our DOPNet, we can see what our initial simulation looks like. Now you'll notice my viewport looks pretty funky right now. This looks seriously wrong, and this is likely due to the scene view getting corrupted and buggy. It's something that I've run into quite a lot actually. So sometimes when things aren't displaying as you think they should, for example, selections might not be highlighting properly or that sort of thing. Sometimes you just need to close the scene view and then create a new pane tab type called scene view. And of course we'll lose all of our defaults. Like for example, I've got my background set to dark, so we have to restore all of that stuff. But now, if we go back to our geometry, you'll see that this looks correct. I'm actually kind of glad that our viewport bugged out on us so that I could show you that quick fix so that you don't get confused when you see it and wonder what is terribly broken in your scene. Now when we display our DOPNet and we go back to the beginning of the timeline and press play, you'll notice that this is going through the frames, but we're not seeing anything visually changing here because we have no forces on this just yet. So let's interrupt this and go back into our DOPNet, and let's add some basic gravity to this. Since this is a pretty big scene, I'm going to start by multiplying gravity by 10. It's one of those things that is very common to tweak. You'll have to adjust that to your liking as we go. And now if we come out of our DOPNet and press play again, you'll see our pieces dropping as we would expect them to. Even with the gravity set at 10 times 9.8, still looks like it's falling pretty slowly. But that's okay for now. At least we have some action happening to verify that everything is set up and working properly. Now let's take a look at some of the guide geometry that Bullet is using for collisions. If we dive in and select the RBD packed geometry here and look at the Bullet data, we can turn on Show Guide Geometry, and this will show you the rough shape that Bullet is using to handle the collisions and interaction for all these objects. In order to illustrate this better, I'm going to go back to my active pieces setup, and I'm going to blast away one of the curved chunks and flip that to delete non-selected so that we only have this one piece of geometry. Now if we look at our bullet solver again, let me stop that from cooking, and we'll dive back inside and once again show our guide geometry. You'll notice that this definitely does not follow the exact contours of that piece. By default, Bullet uses what is known as a convex hull to approximate the shape of each piece. The difference between that and concave is a concave shape curves inwards on itself like so, and another way to identify that is the normals of the object in some areas would project onto itself. That's another way to identify concavity. But this convex hull is pretty much the standard form of collision that's used for most RBD sims. You can totally use other types of collision if you'd like. For example, there's a box approximation, just puts a bounding box around it. There are capsules and cylinders, and you can use compound shapes, which if you have multiple primitives making this up, it'll create a different shape for each primitive, and so on and so forth. And these different collision types would behave much like you would expect them to. For example, even though this geometry is a flat and funky shaped chunk, if we had a sphere geometry for it, this would kind of roll away just like a sphere would, despite its actual modeled shape. So typically for destruction simulations, you'll want to use this convex hull approximation. And this could be subject of some debate because many people come from the school of thought that you should never have geometry that is concave like this, where it curves in on itself. However, personally, as I've probably mentioned a number of times before, my top priority is to get really nice looking fractures to give us a very nice general look for all of our pieces, and we can still handle the collisions in a stable manner. I believe in earlier versions of Houdini, it wouldn't handle the interpenetrations of these inaccurate convex hulls very well, because of course, with all of these pieces being packed tightly together, if each one has a convex hull, there's going to be a lot of overlap between them, as you may remember from when we displayed the guide geometry for the entire fractured area. There's a lot of overlapping stuff. But Houdini's gotten much better at handling that, and it knows not to make everything explode upon simulation. If you remember our very initial simulation that we did, just when we added gravity to our helipad fracture, everything fell, directly downwards, staying intact, and it wasn't jittery or explosive or anything like that. So Houdini's gotten a lot better at handling these kind of interpenetrations. And usually, there's so much going on in a destruction shot, things are so explosive, there's so much flying all over the place, and there's a lot of dust and debris and just mass chaos, that if your collisions are a little bit inaccurate, if you have things colliding momentarily with a surface that's just approximating this overall shape, you're usually not going to notice it because things are motion blurred and covered by secondary elements, and it's usually, in my opinion, worth it to get a really nice fracture and have that trade-off of some collision inaccuracy. Now, speaking of explosiveness in our sims, let's look at how to add some initial velocity to our fractured chunks. Let's delete this blast node that I used to isolate just that one chunk, and start looking at how Bullet stores some of this initial data. Now, each piece of packed geometry is an individual object in the simulation, and we can specify various properties for the simulation with point attributes on these objects. The Houdini docs do a pretty good job of identifying all of the various point attributes you can use to set up these initial properties. So if you look up the RBD packed object in Houdini's help, you'll probably be referencing this an awful lot. One of these first options and the contents points to these point attributes here. And this gives you a very handy list of many of the attributes that you can use to control your sim on a per piece basis. Some of the main ones we'll be interested in are this active property, animated to determine whether the geometry is animated or not. If we look back in the DOP.NET, you'll notice that on this physical tab for the RBD packed object, there's a attribute for density and bounce and friction and rotational stiffness and mass, and all of these things are going to be the same for each of the fractured pieces when you specify it here. But if you create a point attribute on these pieces, that will override whatever this value is here. So if we want to add some initial velocity to our pieces, one way to do that is with the attribute wrangle node. I find this attribute wrangle to be much easier to work with and much cleaner than just using an attribute create node. So if you drop that in before our active piece is null, and then we select that, any attributes that we specify in this little block of code here will be created on the object. So for example, if we type v to indicate a vector variable, and then we'll specify @ symbol v equals curly brace, and we'll just use the values -5, 0, 5. And we'll end the curly brace and add a semicolon. Now, if we look at the spreadsheet for our active pieces null node, you'll notice that this has created a vector velocity attribute that's going -5 in x, it's 0 in y, and +5 in z. And actually, just to make things pop upwards, which is a good test, let's set it to 0, 20, and 5. Now, if we play the simulation, you'll notice that this isn't giving us our upwards velocity that we specified with that attribute. It's still just falling with gravity. Now, that's because we haven't told the RBD packed object to pay attention to that velocity attribute. So if you dive into the DOP.NET and select your packed object and look at the initial state, by default, it's not inheriting the velocity from the point velocity. So if we tick that on, let's stop the cook and rewind. Now if we play that, you'll see that our pieces are launching upwards with that initial velocity that we've specified. It's still not very much. It's pretty subtle because we didn't use a high enough value, especially to compensate for the gravity, but it is working properly. Just to make that a bit more obvious, let's set this to a value more like 100 in y, and I'll just do 15 in z. So we should see a much more noticeable effect from that initial velocity now. Cool. So now let's stop that sim, and let's also look at some initial angular velocity. The angular velocity attribute is called w. It's also a vector. So we can type v at w and set that equal to 3 values also within the curly braces. So let's set it to, say, 5 degrees in x, 0 in y, and 3 in z. Now if we go back and play that, you can see that everything is picking up that initial rotation as well. And this is a good example of what I was talking about before. Obviously, this is maybe a little bit more extreme than our robot colliding with the helipad would call for, but with so much chaos happening, for a lot of these destruction shots, you won't notice some of those collision inaccuracies from the convex Hall approximations. Once you get this kind of stuff happening and some motion blur on there and your secondary elements, you're not going to notice if one of these little pieces in here isn't super accurate with the others. For example, you can see these pieces intersecting a bit, and yeah, there's some inaccuracies, but I think it's totally worth those little bits of interpenetration to get a nice look like this. Another one of the most important attributes that we'll be using is the active attribute. This is a simple integer for, between 0 and 1, 0 meaning it's inactive, and 1 meaning it is active. So to demonstrate this, let's use a conditional statement to set all the pieces to go active at a certain point in time. Our sim starts at 1047, so let's, in our attribute wrangle node, say if at frame, that's the notation that'll give us our current frame, and that's one of those confusing things about Houdini syntax that can take a little bit of getting used to. In some parts of Houdini, you'll use $F to reference the current frame, and these wrangle nodes, you'll use the @ symbol frame to get the current frame. But in any case, if the current frame is less than 1050, we're going to create an active attribute that's set to 0 so that it's inactive. And we can use an I for an integer attribute and type @active equals 0. And then to round out that conditional statement, we'll use an else so that if it is equal to 1050 or more, then the active attribute will be set to 1, meaning that it'll be active and participating in that simulation. Now, if we play our simulation, what we're hoping for is for all the pieces to become active at frame 1050, but you'll notice that that's not happening. That's because when we are overriding bullet attributes with point attributes like this, we have to tell the RBD packed object to pay attention to those attributes that we're passing in. So before, kind of like we specified this option to inherit the velocity from the point attribute, there's another option here to overwrite other types of attributes. By default, this is turned off, but if you check that on, you'll notice that by default, this is overwriting the active and animated and deforming attributes with whatever you're passing in. We can delete animated and deforming for now because we're not using those at the moment. But with this specified, that means it'll pay attention to that active point attribute and it'll trigger our pieces to start when we expect them to. So now if we play the simulation, we should see nothing for the first few frames, but then once it hits frame 1050, then it gets picked up by the simulation and starts moving. Now right now it's just following with gravity and it's not picking up our initial velocity, and that's because this RBD packed object only inherits velocity at the start frame of the simulation. That's a default behavior when using this inherit velocity method like this. So we'll have to get a little bit more creative to come up with an alternative way of adding the velocity to the simulation. Now in Houdini there are many different ways to do many different tasks, but one way that we can use to get our initial velocity working once pieces become triggered by the simulation is to turn off this inherit velocity option, and then we will manually add in the velocity to the simulation when the piece becomes active. So in order to do that, let's disconnect the bullet solver from both the gravity and the RBD packed object, and we're going to use a multi-solver wired in to do this. So if you create a multiple solver and connect the packed object to the first input, and then the output can go into the gravity, and then for the second input we're going to merge in a couple different solvers. One of those is, well, first of all, let's create a merge node to attach multiple solvers. and we'll connect that to the second input. And the first connection for the merge node will be our existing bullet solver. And then for the second input, we'll create a geometry wrangle. Now this geometry wrangle node looks kind of similar to the attribute wrangle node, and you'll use the same sort of syntax for this bit of code here. And we're going to drop in a simple expression to update the velocity at the point at which an object is triggered. Now, since all of our objects are becoming active at frame 1050, we can just hard code that frame value, and we'll say if at frame equals, that's with a double equal sign, 1050, then we're going to add the velocity and the angular velocity to the simulation. So when you have multiple statements in an if statement, you'll need to use these curly braces to define the start and end of it. And the expression will be v for vector at velocity plus equals, so that's the simulation velocity. And we're going to use a point expression by simply typing point. And then the parameters for this are 0 for the first input for this geometry wrangle node. And the attribute we're looking for will be called v in quotation marks. And the point that we're querying will be this attribute point num at pt num. And you can copy and paste that, and instead of v, change that to w in both the point expression and the beginning here. So that'll set both the velocity and the angular velocity at frame 1050. And one more step with this node, if we go to the inputs, we need to tell it what input to use to query the velocity that it'll be adding into the simulation. And we'll use this input 1, and we'll point that to the SOP node that represents the geometry. So we'll connect that to out active pieces. Now if I deselect that geometry wrangle node, it'll check the code that we put in there, and you'll notice that it's giving us an error indication here. That's because I made the simple mistake of not ending the parentheses on this point expression. So when you add that parentheses in there, that error will go away. And now if we play the sim, once again, we're not going to see anything happening for those first few frames. But once it hits frame 1050, then you'll see that it's bursting away with our initial velocity. Now you may be wondering why we didn't set the RBD packed object to overwrite the velocity and angular velocity attributes. And that's because we have a constant velocity set, and whatever we specify here will completely override any sim calculations. So if we were to specify the velocity and angular velocity in the RBD packed object, then that will force it to keep on spinning and keep on shooting away with a constant velocity. It won't be picked up by the simulation forces. It won't be just an initial hit. It'll be a constant velocity. So if you run that simulation here, you'll notice that instead of it just being an initial amount, these pieces just keep on spinning and keep on shooting away with that velocity that we've set. Now, who knows, maybe this could be something that you would want for some sort of effect, but, for destruction simulations, this is not very helpful behavior. Although I should actually caveat that by saying that there have been times when I've done, for example, it was a slow motion shot on a pretty sweet superhero film, and there was lots of debris falling around the character, and that debris is falling in slow motion, and that sort of slow motion falling debris could, conceivably have just a constant velocity and constant angular velocity. So perhaps that sort of very stylized, slow motion, spinning chunks type of shot, you could potentially be handled in a way just like this. I believe for that one I used proper initial velocity, but who knows, maybe the constant update could work for that as well.